Greetings, chemistry friends. So what we're going to take a look at in this video segment, we're going to try to make it as brief as we can. We're going to take a look at two concepts, one called shielding, one called nuclear charge. Basically, what we can break them down to is both of these affect something that we would know as attractive force. So if we were to look at an actual atom, one of the things that we see is that there are charges. Protons have positive charge and valence electrons have negative charge. So there's always attractive force between protons, the nucleus, and the valence electrons. That attractive force might be considered weaker or stronger depending on what type of atom it was. So what holds this concept together? Let's try to relate it to something that maybe is a little easier to relate to. Imagine that we were talking about two magnets. Well, two magnets, when the opposite poles face each other, we would know that there would be some attraction. That attraction, however, would be controlled by how close together those poles were. So if you look at the illustration, there's a stronger attraction here near the bottom where the two north and south poles are closer than at the top where they are further apart. And the distance is what controls the attractive force. And in some way, there is distance that we can relate to in atoms. So these concepts that we're going to talk about, one called nuclear charge, the other called shielding, they're kind of theoretical, but they're very logical. So we can really just relate back to attractive force caused by distance between two things, two oppositely charged things, one of them being a nucleus where there's positive charge, one of them being valence electrons where there's negative charge. So we got this thing, it's called shielding effect. And what it does is it will reduce attractive force when there's more of it. So the greater the shielding effect, the weaker the attractive force. Let's take a look at seeing if we can kind of grasp this. So here's a model for sodium. We've learned to build models already. We know that sodium would need 3 energy levels, or rings, if you will. If we were going to compare a sodium atom to a chlorine atom, what we're going to see is they have the same levels of shields. There are 3 rings for each of these. So the shielding effect is identical for these two atoms. Shielding relates merely to how many energy levels have electrons on it. So if we're thinking about the shielding effect, sodium and chlorine experience the same shielding effect. They have the same number of rings. Lithium, however, when we compare that, lithium actually has less rings. So lithium with less rings experiences less shielding. There are fewer rings shielding the valence electrons. So when there's fewer rings, there is less shielding effect. So it experiences less shielding than sodium. And that would mean lithium has stronger attractive force because the distance between protons and electrons, right, the nucleus and the valence electrons, is smaller when there are less rings. If we look at fluorine, we also only have 2 rings, right? The distance from the protons in the nucleus to the valence electrons when there's only 2 rings is a smaller distance. That smaller distance creates a stronger attractive force. So we'll take a look at how we compare shielding effect between multiple elements in just a moment. So once again, if you look at the bottom here, more shielding levels, the more levels we have of shielding, the weaker the valence electron attraction is. Therefore, we need to look at another concept that affects this attraction. We call that nuclear charge. It's exactly what it sounds like, the charge in the nucleus. The more protons there are, the greater the nuclear charge. So if we look at sodium compared to chlorine, let's take a look at this. Sodium has 3 shielding, or 3 levels of energy levels, 3 energy levels that have electrons. So does chlorine. So sodium and chlorine have the same shielding effect. Well, what is different is chlorine has a greater nuclear charge. It's almost like chlorine has a stronger magnet in its nucleus, and it attracts the valence electrons tighter or with more force than sodium can because of that increased nuclear charge. So chlorine has a greater nuclear charge, but the same shielding effect. Fluorine, right? When we look at fluorine, the shielding effect for fluorine is different than sodium or chlorine. But if we compare that to lithium, fluorine and lithium have the same shielding effect. However, fluorine's a smaller kind of atom because the attractive force for the distance between the protons and the valence electrons is affected by the total protons in the nucleus. So we would say fluorine has greater nuclear charge than lithium, and they have the same shielding effect. So what we can do is we can compare shielding effect and nuclear charge between multiple elements, and we can begin to see it affects the size of an atom, and the size of an atom actually controls, will it give away electrons or will it gain electrons? Its ability to attract has something to do with how easily it will give away. Its ability to attract will have something to do with how easily it can inherit or gain. So if we were to take a look at how to do this, let's toggle to a new window here. And let's see if we can't compare some elements. So let's take a look first at something called nuclear charge. So let's mark up our text box as nuclear charge. And we're going to list these in an increasing order. Which elements have lower nuclear charge, which have higher nuclear charge. And then what we'll also do is we will list the same elements in an increasing order for something that we would call the shielding effect. So we'll pick out 4 elements and we'll kind of model how we can compare them. So the shielding effect versus the nuclear charge. So let's just highlight some elements on here. So we'll highlight lithium, we'll highlight carbon, we will highlight calcium, and we will highlight bromine. Let's compare them in an increasing order. Increasing order would mean lowest to highest. So let's go first with the shielding effect. The shielding effect is controlled by how many rings. So what we do know is that carbon and lithium both have the same shielding effect. So if they have the same shielding effect, it's going to be difficult for us to tell apart the influences of shielding between carbon and lithium. So maybe it's not such a good idea to compare them in the same period yet. So let's take silicon and let's take bromine. And let's start this conversation right out of the gate by looking at the shielding effect. Okay, so here we go. Shielding effect. The least amount of shielding would have the least rings. Lithium has less rings than silicon, calcium, or iodine. So the next would be silicon. Silicon would require 3 rings. So the shielding effect would be a little bit greater. Calcium would require 4 rings. So the shielding effect would be a little bit greater. Iodine would be a very large atom compared to these others. The shielding effect would be very strong, or very, it would influence this very well. So the shielding effect, from lowest effect in shielding to highest effect, there is the ranking order. Nuclear charge, we really just look at the protons. The more protons there are, the greater the nuclear charge. So we could kind of see that we actually have the same sequence for nuclear charge. Let's compare nuclear charge for elements all in the same period, and I'll speak briefly about why we might want to think about considering that. Okay, so we're going to put these in an increasing order for nuclear charge. Nuclear charge has to do with how many protons are in the nucleus. So the one that has the least amount of nuclear charge would be lithium. Lithium has less attractive force in its nucleus, right? Carbon would then be next. Oxygen would be next. Neon would be our last. So the nuclear charge has something to do with attractive force. The more nuclear charge, the more attractive the force is for valence electrons. And this is kind of how we compare ideas that relate to attractive force. The greater the nuclear charge, the greater the attractive force between valence electrons and the nucleus. The greater the shielding effect, the weaker the attractive force between valence electrons and protons in the nucleus. Until the next time, this is Mr. Brewer.